don't know. We want this to connect? We, yeah. Yeah. But I don't know whether, yeah, allow, I guess, here. Oui, I think, do we need to set up the whole thing here?
Because this one is not yet, we have to connect this also, that one section.
Oh.
Because this is only for the pointer and this is now for the display.
Should I close it?
Yes.
I'm not good in all these kind of things. Yeah, is this the thing I need? I guess,
Yes. You can see here.
Yeah.
If you want to mirror, extend the entire screen.
Yeah.
No? Mirror this window, okay?
Yes.
Thank you.
Now, sure. Enable the pointer and the next slide. Yes.
This here?
That's a little bit. And the cable, if you can put that in the pocket, and when you plan to talk, you move this. You can do it now. No, to talk. Right now it's muted. Now it's you're talking.
So welcome everyone to the second day of the workshop. We start with Professor Anne Nowé. Very happy to have you here. Professor Anne Nowé is a professor in both the computer science department in the Faculty of Sciences and in the computer science group in the engineering faculty at the Vrije Universiteit Brussels, Belgium. She did her PhD again in an interdisciplinary topic in the intersection of computer science, control theory, fuzzy control, and mathematics, numerical analysis, stochastic approximation. So very apt. And she also coordinates the project Control XAI on automated controller generation at the intersection of control engineering and machine learning.
Thank you. Thank you for the invitation. Yeah, when I was invited to give a talk, I thought, yeah, maybe I can start with some lessons learned in this interdisciplinary collaboration. So I also collaborated in a previous project where AI people were collaborating with control people. So I will start with some lessons learned, or also how I looked at the collaboration so many years ago. So the first project I'm going to refer to was, I think, from 2009 till 2013, something like this. And then at that time, I very much had the impression talking to control engineers. So that's the name of the project. LecoPro stands for Learning Production Machines. And of course, Gen AI, the image is generated, but I very much had a feeling like once upon a time there was a model. And why I'm saying this is because within the project, we were pushed to compare reinforcement learning with classical control techniques. And there's, of course, two issues with that. If you want to apply RL to also a setup where classical control theory is doing a perfect job, there's no real need to do reinforcement learning, right? And then another issue was that these control engineers were always asking, but how many interactions, samples do you need to train your models? And then I was asking to them, but how did you come up with your model? And of course, you can do it sometimes from first principles, but if you do model identification, you also need samples, of course. And then I never got a real answer, because it was like, we don't know anymore. We have this model laying around already for many years. And that's why I'm saying here, and it gave me the feeling of once upon a time, there was a model, and then we continue, but we forget the whole effort that has been done to actually get to that model. You also have to see it in a context. I'm referring here back to the project 2009, so like 15 years ago. At that time, when you were doing reinforcement learning and you wanted to have something published on your algorithm, you had to show that your algorithm was working without any prior knowledge. So a lot of older work on reinforcement learning have to see it in that context. So it was probably a bit of time where this was shifting, but today we hear a lot of, you can do some physics-informed techniques and so on, which are, of course, really fine. We also heard them yesterday. So this is, of course, what you want to do. If you want to go to challenging applications, you should not throw away domain knowledge, but this is not how people looked at the field of reinforcement learning that long ago. That long ago was really like, okay, can you show that your reinforcement learning algorithm is learning from scratch without any prior knowledge? So that was a challenging situation. But then during execution of the project, we managed to move to some setups, real setups that were very hard to model. And here you can see two of them. So the left one is a weaving machine. That's from a company, Picanol. So they built these machines and they ship them all over the world. They're really one of the main manufacturers of these weaving machines. And the challenge is, of course, that you make such a machine, but then at the end it has to work with different materials in different conditions. So it's not easy to fine-tune the machine or the controller on the machine. I don't know, if you need to send over technicians to do that, that's too expensive. So they really wanted to have some system that could self-adapt or that could adapt to different situations. So the material that is being made, as well as the environmental conditions like humidity and so on, have an impact. And the way these machines, so that's one here at the left-hand side, is working is, so the material is blown to the other side. So that pressure should be just strong enough, not too much, because then you have like overshoot, and if it's too weak, and the thread, the material will not cross to the other side, and then there's also a problem. And we use a kind of bandits for this on continuous actions to solve that problem. And this was at the end, after the project, it was actually implemented. So today, some of their machines are running with this basic reinforcement learning algorithm on the machine. The other one is a wire winder. So it's from Bekaert. So here it's the wire is, how do you call this? It's not, yeah. They make steel. Is that, yeah? So it's the whole challenge of doing this winding is, so they make this steel wire, and then they have to wind it on this bobbin. And the more material you put, the flanges start to bend, and that is the challenge, and to control this system. And so we really had to come up with, an approach to apply, on the one hand, reinforcement learning, because it's very hard to model this system. But here the main challenge was to come up with the good reward scheme, because that's maybe another message. So very often, to my opinion, you explain to people of industry how reinforcement learning works. You say, you need a reward scheme. And then they try it out and they say, well, this reinforcement learning doesn't work. But then if you see how they actually define the reward, then you see, if you're a bit trained in defining reward schemes, that they didn't do it the proper way. And of course, then the controller doesn't behave well. So that's maybe a second message. You need to be trained in coming up with a good reward scheme. So here, how we did it was, so two things can happen. So two problems, the one at the left-hand side and the one at the right-hand side. The middle is fine, because then you have a very nice flat surface. And that's very important, because at the end you have to unwind the bobbin if you want to use the material. Therefore, the objective is to have it as flat as possible. So you can have two problems. You can have like what they call a hill or a valley. And how can you detect that? Well, of course, you could maybe put cameras watching the surface, but that would all be way too expensive. So how we did it is by measuring how much of this wire was used in one sequence to go from the left to the right or from the right to the left. And if you have a hill, means that you have a bit more, you use a bit more wire than what you expect. If you have a valley, you use less wire than what you expect. So you get this delta P. And this could then be translated into a reward scheme. So to punish actions. So if you have a hill, you really want to have your delta P is positive. So you want to give a negative reward, because if the action is going too much to the left, you want to punish it. You want next time to not go that far. But if you have a valley, you really want your action to put some material where the valley is. So then the delta P is negative, and with the minus sign, it will be positive. So then you want to encourage the thing to go a bit more towards the edges of this bobbin. So here the message is mainly, well, defining a reward scheme is not always obvious. It can go wrong. You also have constraints of what you can use, which signals you can use. Some, like I said, putting a camera would maybe be an alternative, but way too expensive to deploy this in practice. Okay. Within that same project, we also looked at autonomous driving of tractors. Because we also have some manufacturers of these tractors in Belgium. And they wanted to have a system that could drive autonomous on the fields. But there the challenge was not so much, I will show it on the next video, like in a lab setting, it worked all fine, like in a toy version of this. But the problem was that you need like GPS coordinates, And again, this is like 15 years ago, and that signal was absolutely not accurate, way too noisy, way too much delay. I think yesterday we also heard in the talk of Jens the problem of if the system, the signals are delayed, it's very difficult to be robust against that. And that's also something we experienced like 15 years ago. We have never been able to deploy this at that time, 15 years ago, in practice. So, but another element that I want to stress here is the way we organized the reinforcement learning algorithm. So it was a fuzzy version of a Q-learning algorithm. It's maybe also a nice reference to the first talk we heard yesterday morning. So basically, that's a kind of linear interpolation that we're doing here as an approximation technique. So that's where everything can be proven to still nicely converge. And so that was one element. And so to be able to deal with continuous states and also continuous actions. But we also wanted to have a safe approach in the sense that, of course, you don't want these structures to drive all over the place. You want to have a decent performance right from the beginning. So we used a PID controller as a backup, and that would like supervise the reinforcement learning process. And the trajectory, one of the trajectories that we used to train the system was like performing this kind of 8 pattern. And you see where everything, where the dots are red, that's where the reinforcement learning algorithm is taking the action. So where it is sufficiently certain to decide on the action. Where it is yellow, that's where the RL algorithm would say, well, I'm not convinced about my Q values, basically. So then it was the PID controller taking action. And then the green you see over there is where the RL agent was, yeah, like doing something which was too far away from what the PID controller would propose. So therefore, safety reasons, it was also overruled. And here you see the lab setup. So we made a small Lego kind of thing. So there was a camera watching the tractor between brackets. And you could see on the screen real time which component was taking an action, whether it was the RL agent or the PID controller, and you could also see it gradually improving over time. So like in the lab, everything went fine when we were testing it, but we also did this on the field with this tractor, and as I already said, it never managed to learn well, something sufficiently decent to be deployed, but this was due to the GPS signal that was experiencing too much delay. Now, 15 years later, and they have redone it, and they got much better results than what we had at the time. So here maybe the message is, well, AI applications and the success of an AI application very much depends also on other technology. And I think self-driving cars are also a nice example of this. If you look at the evolution of self-driving cars, I don't have a video here, but if you want to see it, I have a video of a self-driving car, actually a van from the 80s when I was a PhD student, late 80s. We were seeing demonstrations of self-driving cars, but it was basically a van because everything had to be on board on the car. So to put all these computers and so on board, it had to be a van and it could not be a car. 10 years later, you see demonstrations of self-driving cars that not only drive much faster, but also or just regular cars, because then computers became much smaller. This is another example, so much more recent. also related to Safe RL. So this is a result from a PhD student who's doing a PhD jointly with a company. It's the company ABB. And it's in the context of multi-energy systems. So that means you have a complex system, so to say, with different components, different sources of energy, and they have to be balanced. And we also used reinforcement learning to control this system because it's quite complex to handle. And we wanted to improve on MPC, so model predictive control, which we managed to do. And you see there pseudocode of 2 algorithms. Again, because you want to deploy this on a real system, you have to make sure that even during the learning process, the RL is not doing crazy actions. So there was on top, and that's called a safe fallback, where if the action that is being proposed is too much out of range of what your traditional control technique that is currently used would propose, it's overruled, and that's just what is happening on top. But then the second version is where every time the RL agent is being overruled, it's also considered to be like a negative reward. So it learns to avoid this overruling, and therefore at the end it learns a safe policy without getting out of bounds anymore. That's in a nutshell what is happening in the second version of the algorithm. But also here, even when we can show that on simulators the company is using, we can show that it improves over MPC. It's very hard to convince a company to actually deploy that controller in real life. In a current project, I know I have another example which I also like. That's from colleagues of robotics. I have here a movie. I will show it to you. I find this a nice example, and it's a completely different idea of safe reinforcement learning. But here, it's the robot arm that like signals to the human. So each time it's becoming red, it's like saying, I have seen you. I know I'm too close to you. I've seen you. I will back up a bit. So I find this an interesting idea that the algorithm is signaling to the user who has to collaborate with the robot that, okay, it's fine, I saw you. I find this an interesting idea that I also wanted to share with you. Within the more and the current project that was mentioned in the introduction, so it's a project that we do together with the University of Ghent. In Ghent, these are more the control engineers who are familiar with reinforcement learning. But within this type of project, it's called SBO, it's Strategic Basic Research. You have a user committee. So there's a user committee of about 15 companies. And here we did also a survey to know how advanced the companies are in using AI techniques. And I will just show you a part of the survey. So what you can see here is that, well, the majority of the companies, okay, it's Belgium. We have a lot of SMEs, so we don't have so many very big companies. Belgium is a country with a lot of SMEs, but you see that, and it's also a small sample, of course, and we had 13 people in that workshop, or 13 companies, I should say, 13 people representing 13 companies, that you see 3/4 of, or 77% of the people are just using still the classical PID controllers. There's only like half of them doing a little bit more advanced things of combining a PID controller with some other techniques. Only 1/4 is using model predictive control. Maybe a bit surprising that half of them are using a kind of rule-based setting, and 1 out of 4 had experience with using some machine learning techniques, but that is a flexible thing in the sense it could also be machine learning, for example, to do model identification, not so much for the control. If you another part of the survey, so what you see here is that 9 out of 10, 91%, is actually still tuning their PID controllers manually. Yeah, so that was also a bit surprising for us. Some use the second line, classical control tuning techniques, more using some guidelines to fine-tune the PID controller, and some were using machine learning techniques to do that. So this was for us a bit the context of, okay, what is the state of play of these companies we have in our user committee. Another thing that came out of this questionnaire is this word cloud. So now I'm going to talk a bit about, on the one hand, there's this education. So we also found out that for these companies, it's very hard for them on their own to decide whether or not reinforcement learning can be an added value to their current approach or not. And then you see things like safety, transparency, verification, so explainability, so that's all a bit related to trustworthiness, and I'm also going to talk a bit about that. Of course, performance, accuracy, yeah, that's something that is really needed. If you cannot guarantee that, no way they will deploy your controller. So to address the thing of education, so referring to mainly, can you explain me when I should use reinforcement learning or when I should stick to the classical approaches, which, yeah, if your problem is well suited to apply these classical control approaches, of course, you just should stick to them. We made this kind of flow chart, and here on this part here is referring to whether or not you should use like reinforcement learning or not. So it starts here. So the first question is, do you have a model? If you have a model and it's a simple single input, single output system, then you can consider your PID controller. But for example, if there's no model and if it's hard to build that model, I think then we can go here. We need a repetitive task to apply reinforcement learning. No, I don't know really why it says no here. I should look to the PhD students there, but I would say, yeah, okay, iterative learning, but well, you need some trials, of course. So for me, this is repetitive control. You need some trials to actually apply your reinforcement learning. So there should be some semantic thing there. But okay, the main message here is what we noticed is that in industry, well, you have to help people making the decision of when to use which techniques, especially if you want to incentivize people to use things like reinforcement learning. Yeah. 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 So you're right. So if there is a model, but can you repeat the second part of what you're saying? Yeah, I think here somewhere, nonlinear MPC, but I think this is maybe a bit covering what you're saying. Here?
Yeah, but I'm also referring to the case when it's just for computational reason.
Yeah, it's. I agree. I mean, the flowchart can still be improved. It's a first version, but my message is mainly we should help with this kind of flowcharts, and we actually already had quite some discussion on it because before you know it's becoming very, very complex as well. So maybe a flowchart is then not the ideal solution to give all these nuances and details, but definitely we have to find a way to be able to show or to give guidelines of when to consider more advanced techniques. But the project is 1.5 years, I think. So and it's we need to still improve that, but we need something like this. Not only to my opinion, but also and the colleagues within the project. So we felt the need for this. Of course, sometimes it's very hard also to answer the questions from industry in the sense of how many samples will you need? That's a very tricky one. So then how much will it cost somehow? Because collecting samples can have a kind of price. How much time it will take. These are very hard questions to answer because it's a whole interplay. I already said the reward scheme is an important one, but it's the reward scheme and combined also with the kind of reinforcement learning technique you apply that it will also have an impact on how many samples you need. So, but this is the kind of thing we would like to develop, but it's good. This is a workshop, so I thought I can also show things which are not finalized and which we can discuss. So any input on this is of course welcome. Okay, then within the project we are exploring different approaches. This is a technique that the University of Ghent is very much applying residual RL, where there is a basic controller, and then the RL agent is, let's say, correcting somehow, and that action is putting an action on top. It can be adding, it can be other kinds of combinations. Sometimes it works very well, but it can also be still challenging to make this work. And our experience is especially when, let's say, the features that the RL agent has to learn are non-trivial, then learning this residual part can also take a lot of effort, and it can be actually faster to just do plain RL. So whether or not you will gain if you do residual RL very much also depends on the complexity of the features you need to express the controller. Sim2Real is something that yesterday was considered or very much already discussed. So I'm not going to go in that one. This policy learning refers to learning parameters of your controller using RL. So for example, the gains in the PID controller. Then we can have offline RL, so where we collect data using the current control strategy, of course, with sufficiently exciting the system somehow. But that means that we don't need to actually apply the RL strategy to learn it. That's the offline RL part, and then other combinations of control and and RL are considered here. But now I want to go to some aspects of, well, what you could call trustworthy RL. So that can be transparency, interpretability, explainability. These terms are not always used in a very consistent way in literature. And so the umbrella term is more trustworthy RL. And there's different aspects to it. So first I will focus on what I would call more transparency. So today, but maybe Frans will talk a bit about that this afternoon. I don't know about, because he also worked on explainability and things like this a bit. Might pop up, but I will, well, to my opinion, and for the moment, we very much have what I would call rule distillation. So expressing the control strategy in a set of rules or some other transparent format. So here you see an example like in a computer game where we have this Mario who has to collect coins. So here there's a variation of, I think, the standard game in the sense of that the coins have colors, and some colors give more reward than others, or some coins should not be collected because they even lead to punishment of the agent, and that's the setting. So you can train an RL agent on such a system in such an environment, and then translate the policy that the RL agent has learned in some symbolic, interpretable, or transparent format. Maybe before I forget, I can already mention something. If our experience is also that a tricky thing here is to what extent the environment is really an MDP. So we also heard this yesterday. So the more your environment is an MDP, so is Markovian, and the easier it is to apply reinforcement learning. But many RL techniques are rather robust to the environment not really being Markovian. I'm now not talking about POMDPs, partially observable environments, but just it's in principle observable, but it's not really, strictly speaking, an MDP. And then your RL algorithm will still behave decent. So it's graceful degradation, as we call it. But if you then translate it into a set of rules, then it can become tricky. And then this little, kind of robustness you need to be robust against this not really being Markovian, and can completely break down. So here, and it can also be how the environment is represented. So here in this case, for example, with this Mario game, I'm not at all a Mario game player. You have this little thing here, enemy, I will call it. So what happens in these environments is Mario is, for example, jumping on it, it dies. So visually, you see the enemy is dead and you should not bother about it anymore. But how the RL agent is perceiving the environment, it's like still there. It's still part of the state space. And for the RL algorithm to learn, it can jump on the enemy. It will be dead, and then it can continue. And it's fully robust against that. But once you translate it into rules, the difference between the enemy being there, but the enemy being there, but dead, is not made. So that can all be tricky things if you do this rule distillation. Another work I want to cite is this action influence graphs. So I've put the reference there. That's not our work. So it's in a StarCraft environment, and that they tried it. They also have other applications. But the message here is, well, if you have a kind of causal graph, so some domain knowledge, of course, and then you can come up with richer explanations of the control strategy. So here, for example, they managed to have explanations to questions. So here you see, and this is the goal, let's say. So these are two goals because these ones and these states are generating rewards. And if you look at the graph, what you can do is you can either go this way and then to increase this values of these two states to get more rewards, or you could go this way and then it joins here. That's another strategy to get higher values in these two states. But through RL, you can learn that this is the more efficient path to take, and then you can answer questions like, this is apparently building barracks, this action here, building barracks is here. So then it can say, well, it's actually better to go here, supply depots S, because you will be able to increase these values, like say, in a more efficient way. Yeah. Excuse me?
It's a multi-player game.
Yeah, yeah.
So I would expect the information to take into account the strategy of the opponent, but that's something.
I don't think it was already so sophisticated. Yeah, yeah. I think maybe if they can extend this causal graph, taking into account the opponent, and probably they can use the same framework. This is indeed from the single agent point of view. But the main message is, sometimes you have in your environment some ideas of causal relationships, and if you can express it, then you can use it in the explanations, and you can have, let's say, more grounded explanations than just having a transparent model like this one. Yeah. But I think we really would like to have is something, and this is mountain car, so traditional benchmark for RL, so the cart has to swing and to be able to get up the hill. So the real explanation, to my opinion here, is I'm building up momentum. And this is not, of course, easy to generate as an explanation because you need to, well, know what is momentum. You need to have the insight in physics to be able to generate such an explanation. But I think this is what we really would like to have. And today we basically have this kind of, let's say, rule-based explanations that make the policy transparent, but not really explainable. Visualization is, to my opinion, just like with a mountain car, a good tool. This is a strategy that was learned by this work, local advantage networks for multi-agent reinforcement learning, by one of my PhD students, Rafael Alvalos. So he came up with a strategy that allows, in a nutshell, to do what we call today centralized learning, decentralized execution. But the new element was that he was able to do this, allowing agents to learn some diversity in their strategies. And you will see it when I will start the animation, what I mean by that. But to understand what was now learned, we could see it got more reward. It was able to handle difficult environments. This is, I think, called corridor in this game. But we needed a visualization to really understand what was being learned. So we'll start. Oops, no. Takes a bit. No, takes a bit of time to start. Maybe I can do it like this. Yeah. So what you see here is that one agent is sacrificing itself to distract these blue enemies. And they're still enough to kill the blue enemies you saw on top. And now they just get close enough to the blue enemies to attract some of them, and not too many, otherwise they would lose. And at the end, they will have killed all the blue enemies and able to cross this corridor. So that's where they reach their goal. Yeah? I think this is not something we can explain today, just looking at executions of the policy without this visualization. And the visualization here really helps to understand what is going on. Still have a bit of time to mention some other work that we have done. So not these very rich explanations, but for example, we used feature importance by training a soft decision tree on a policy learned by reinforcement learning to understand what are now the most important features for to condition the action on. So this is what is called a post hoc approach, and that's maybe also important to mention. So you basically have two strategies. You have your reinforcement learning agent, you give it a full freedom, and then you try to understand how the policy works, or you make it interpretable by design. So we'll also show you something on that later on. But here this is post hoc, so it means we have a policy and we try to gain some insights in the policy. And one way to do it is with this soft decision trees. So soft decision trees are like regular decision trees, but only the decision nodes are like small perceptrons. So they're a bit more complicated than regular decision trees. And the idea came from visual tasks, where, for example, handwritten digits had to be recognized or correctly classified. So we also use that on our Mario game to better understand what is Mario basically looking at to condition its action. And then if you take a policy and you train such a soft decision tree, you can get things like this. So at the top node, what is most important is the object that is just above Mario a bit to the right, and depending on what this value is, and then it will, for example, be important that Mario knows that it's, for example, standing on the floor and not already jumping. Things like this can then be understood by training such a soft decision tree. Something else we did is this rule distillation. So again, you take a policy trained potentially by deep RL, and then you try to understand the policy that is being learned. But here we wanted to get a set of rules. And for this, we adapted, so we changed or we made some extensions to rule mining algorithms. So the idea is, so what you see here to the left is a greedy policy learned for mountain car. And here my message is, so if you look at this, so there's three actions, right, no force, and left. This is like the trajectory that is being taken. Well, you see this, yeah, you could call it kind of noisy actions. So this is the greedy action, but you can wonder whether, yeah, it's now really necessary here to have no force instead of right. But this is what you typically get if you train an RL agent and you would just look at the greedy actions, that it would be a bit noisy. Or phrased differently, the optimal action you see according to the values, the optimal action just has a value which is slightly bigger than some other action, than the value of some other action. So you can do a kind of regularization. And this is what you see here at the left. So you can clean up your policy a bit, regularize your policy a bit, but instead of saying I want to have a smoother representation, it's really driven by the performance, by the reward. So it's not saying, okay, this action here, this one, this green one, can as well become yellow because it's surrounded by yellow actions. It's more like, okay, this green action here is only slightly better than the yellow action, so it can as well join the yellow actions. That's the idea. It's driven by the performance. And for this, we adapted a rule mining algorithm. So I first briefly explain you how this rule mining works, because you might not be familiar with it. So most rule mining algorithms, not all, but the majority would work like this. So you would have data, data here, data here. So it's two classes. So a rule mining algorithm would try to identify an area of only, in this case, purple dots. So it would like to find an area which is as big, as large as possible, but also as clean as possible, only having dots of one class inside. So it's support, that's the area, and accuracy is how clean is the area, basically. So then it would learn this rule and it would put this data aside, so that's covered by the first rule, and then it would start to search for another area. And so here, and that could be a good compromise of being rather big and being rather clean. So that's the basic idea. Okay, these are my animations. So now if we translate this to the problem we have, so the idea would be, so now we have three labels. So and that could be my three actions from my previous slide. So blue means the best action, the greedy action is really clear. It should be blue. Orange means the greedy action is really class B. Yeah, so it's very outspoken. But then you have situations where you have green dots. It's of course a synthetic example here, where the greedy action, well, it's not really clear. It could be A, but B is almost as good or the other way around. So the green dots are basically happy to join whatever class. And if you take this into account in your rule mining algorithm, you would get a very simple set of rules here, and that can express the optimal policy. So here I have a little example which are called muddy world. So the idea is, it's of course a very simple toy problem. So suppose this would be the start state and this would be the goal. So we need to have a policy bringing us to the goal here, but here is a muddy area that should be avoided. Once the agent gets there, it's stuck, it's difficult to get out. So a greedy policy could be something like this. And if we would, again, just apply rule mining on this, we would get quite a lot of rules because, well, you can argue, why should we go here to the right? We could as well have gone up. So we can, as I explained on this synthetic example, clean up the policy and basically get something like this. This gives you a high-level view on the policy. It's not optimal, Yeah, that's probably your question. Yeah, it's forgetting details. So that's so if you would do rule mining on the greedy policy, but some of them are happy to join this direction instead of going up. you could get something like this. And this will, whether or not you have these details, will really depend on hyperparameters of your rule mining algorithm. But the idea is, okay, let's get a high-level view of the policy, and then, of course, in this case, the approximation is way too coarse, and you lose quality of your policy, you lose reward. And well, if this drop is too high, you can do like a second phase and get some more detail, and then you would be able to model the ways to avoid the muddy area. So it's like a high-level view, and you can zoom in and get more details of the policy. I don't have time to go into too much detail on the algorithm, but it's really driven by reward, not by approximating the policy, but by how much reward do you lose, how much is the drop in quality of the policy. And that was how we did this. So this is like post hoc. You give all the freedom to your RL algorithm, and then you try to synthesize, you try to get some insights, but we can also have, let's say, interpretable by design. And this is also not work from us, but colleagues of the University of Leuven and some colleagues. But I find it interesting, it's called relational reinforcement learning. So the whole idea is you have a kind of, well, symbolic relationships, and it's here illustrated in the well-known blocks world in AI, where you then apply reinforcement learning to come up with an optimal policy. So the operators, the descriptions of the states and so on, and they're all symbolic. You can understand them. However, the tricky part here is it's not always easy to get the good relationships to make the problem sufficiently Markovian to the agent. That's where the real challenge is. What are the relationships you need? Of course, like in the blocks world, we know, but in other applications, it might be difficult. So it's a nice idea. However, the tricky part is, well, what are the right expressions, relationships you need to make it sufficiently Markovian for the agent to be able to learn to solve the problem in an efficient way. And within the project that I was referring to, this control times AI, we adapted a bit the idea. We try to improve on this, and this is the work of Senna, who's sitting there. So if you want to have details, you can talk to Senna. And the idea is a bit to revive, old ideas of genetic programming. But genetic programming is, of course, like genetic algorithms, but you evolve a program, and a program can be something symbolic. And so here you see the typical genetic algorithm loop. So you have like your population, you do selection, crossover, mutation, and then you have to see how fit your individuals are. And if those are control strategies, well, you can evaluate them by applying them in your environment, can be the real environment or a simulated environment. Yeah. But the genetic programming is also known to not be very efficient. So the good thing is that you can have symbolic representations of your program. So what you then do is you encode somehow some expressions. So depending on your field of application, you can think about what are meaningful ways to express your controller. Here it's just an arithmetic expression. It could be basically anything as long as you can encode it. But just to apply genetic programming on this would be quite inefficient, often very stuck in suboptimal solutions. So the idea was, let's combine it with a reinforcement learning ID. So here we basically have the reinforcement learning loop, which you probably all know. And to be fast on this, again, Senna can give you much more explanations. The idea is that we have an actor-critic approach. So here the critic can evaluate the control strategy, but the critic can also propose alternative actions for certain states. And this is how you can also improve your individuals. So you basically have a combination of an evolutionary process and an RL process that is more efficient in evaluating the individuals. You don't need to run your full controller in the environment. You can have, through the critic, local improvements. And the critic can do this for all the individuals. So that's where you really gain in the number of evaluations you need in your system. And one more slide just to conclude. No, that's an illustration. Yeah, so it's the cartpool problem. So this was the program that was synthesized, and here you see the whole thing in action. What is maybe interesting to watch is that you see the symmetry in the problem is reflected in the symmetry in the control strategy. What you can also see is, and this is still like future work, the carpool is slightly, gradually drifting towards the left-hand side. So whenever it's a bit exaggerated, so this is the simulation here. So this is like magnified, amplified, and this effect. So it's not so bad, but I think we still need to improve the technique in the sense of rare samples. So rare samples, or maybe the starting positions of the cart, or when it starts to drift, or not sufficiently taken into account into the distilled policy here, in this one here. So maybe we need also to have the idea I explained previously to maybe have a more hierarchical approach later on. And this is the last slide I wanted to show, because it also refers back to a talk of yesterday on providing formal guarantees. It's a bit different to the talk yesterday. So in a nutshell, we distill the model as well as the policy. That's the difference from the talk that was given yesterday afternoon, I think it was, where only the model was distilled and then the policy was learned through model checking. What we do is we distill the model as well as the policy. So that means we make abstractions. Also driven by this B simulation approach that was explained. And then we have a discrete model as well as a discrete policy, where we can do the model checking of the policy in the discretized model, the discretized MDP, basically. I just wanted to mention that because it connects to the talk of yesterday, and I will conclude here. It's maybe a bit too much. Yeah.
Control has to have a safe fallback.
Mm-hmm. So it's referring back to the yeah. So it's the signal where each time you overrule the action is actually a very strong negative reward, because you really want the agent to learn to avoid being overruled. And but I think it's well known, and in the sense of if you have for example, MPC, it has a certain given time horizon. So it has difficulties with problems where the horizon is too short to actually see it's going to fail in the future. And this is the advantage of using reinforcement learning, because you can back propagate that signal so it learns to avoid being overruled. And this is the strongest signal, and that's like the first objective, you could say. And then the other objective is, let's say, the normal performance of the system. Is that answering with your question? Yeah.
Yeah, so thanks, on a really great overview, really tour de force. I was actually wondering a little bit about your perspective on perhaps something slightly less technical. I was triggered by you talking about most companies, etc., using their PID controllers. It's kind of hard for them to deviate from this. So I presume that moving towards machine learning or reinforcement learning could offer actual benefits.
Yeah.
But so apparently it's too hard to explore these in kind of like small bottom-up projects, if you will. So yeah, do you have any idea like is there something that we can do? Perhaps it's more like a political kind of question almost, but something that we could do, the machine learning community in the Benelux to somehow overcome this kind of pressure.
I think this kind of like the work I've shown on energy, where it's really in collaboration with the company, is I hope in the future we will be able to push it a bit further, and it will be deployed. Because there, the good thing is that the PhD student is an employee of the company. Well, of course, we cannot really predict the long-term future, but the idea is that this person will stay at the company. So I think that's also very important. I hear a lot of companies as well, like, okay, you give them an AI solution, but what people forget is that an AI solution also needs to be maintained. So it's not like, okay, I give you some piece of software or a solution, and then it's up to you. And of course, at universities, then we move on, or the PhD student who developed it, is yet at another company, or so. A way to maintain the solutions is also very important, and that's maybe also an element in the decision of not adapting the solution, because they are afraid that they will have a solution nobody in-house understands. So doing PhDs in collaboration with companies, but sometimes that's also here. That was a very fine relationship we had, very respectful for the work the PhD has to do to come to a PhD. Unfortunately, that's not always the case. So I have a bit mixed feelings sometimes about this kind of PhDs. It all depends on respecting both sides of the work that needs to be done. But also move to problems that maybe, like in the weaving machine, it was quite easy because they didn't have a solution, you see. So it's better to have something that they see performs well, while they didn't have the answer to the problem. Yeah. But I hope that, but that's maybe, this whole idea of like CERN for AI. I think we need to indeed join forces to showcase really interesting applications that maybe individual groups cannot really tackle. And I think that's where we get the competition from, let's say, the big tech who can do this. So there I would like to see more joint challenging setups where we can really make the difference. That would be nice, to my opinion.
We have a group photo, then we meet back at 11:30. Just outside.